This video is for Chemistry in the Earth System, Unit 3.2, Ionic Bonding. Today's essential question is, how is electronegativity used to determine which atoms form ionic bonds? Our first main idea, electronegativity. Which elements are likely to form ionic bonds as opposed to a covalent bond or a metallic bond? The answer depends on the electronegativity of each element. Electronegativity is a measure of the attraction of an atom for electrons within a chemical bond. If the difference in electronegativity between these two atoms is 1.7 or greater, the atoms will form an ionic bond. For example, fluorine, which has an electronegativity of 4.0, will form an ionic bond with nickel, which has an electronegativity value of 1.8. The difference between these two values is 2.2. On the other hand, phosphorus, which has an electronegativity value of 2.1, will not form an ionic bond with nickel because the difference between these two values is only 0.3. In general, elements with the lowest electronegativity are found among the metals in groups 1 and 2 in the periodic table. Elements with the highest degree of electronegativity are found among the nonmetals, especially those in groups 16 and 17. As a matter of fact, the element with the highest electronegativity, which is 4.0 as a value, is fluorine, which is located at the top of group 17. Our next main idea, crystal lattices. Compounds held together by ionic bonds form three-dimensional geometric solid shapes, which we call crystals. The atoms of an ionic compound are linked in a particular structural pattern. The structural pattern of atoms is called a crystal lattice. In sodium chloride, for example, atoms of sodium and chlorine form a lattice that produces a cubic crystal. A variety of crystal shapes are produced by other ionic substances. The shape of the crystal is determined partly by the ratio and sizes of the positive and negative ions within the compound. Because multiple ionically bonded atoms are attracted to each other in a crystal lattice, they do not form individual molecules. The smallest unit of an ionic compound is called a formula unit. This is the smallest whole number ratio that exists between the cations and the anions in an ionic compound. Crystals tend to be brittle and have high melting points and boiling points. For example, the melting and boiling points of sodium chloride, which is NaCl, are 801 degrees Celsius and 1413 degrees Celsius. Those of lithium fluoride, which is LiF, are 870 degrees Celsius and 1676 degrees Celsius. In general, the stronger the ionic bonds between atoms in a compound, the higher their melting and boiling points. Based on this principle, scientists have determined that the ionic bonds holding lithium and fluoride ions together are stronger than the ionic bonds holding sodium and chloride ions together. Another characteristic of ionic compounds is their ability to conduct electric current when melted. And please remember that only when melted, not in the solid state. The cations in that molten or liquid state flow to one electrode and the anions to another. This produces a flow of electricity. Ionic compounds also conduct electricity if they are dissolved in water, because in this instance, the ions are free to move within the solution.
Ionic crystals, their structure and properties. Objective: to learn the basic structure and properties of ionic crystals. Ionic crystals are a special class of crystals, unique in that their oppositely charged ions are bound together by an electrostatic force of attraction. In these crystals, The positively charged ion is known as a cation, and it comes from a metal. The negatively charged ion is known as an anion and comes from a nonmetal. To better understand these structures, let's look at three common examples of ionic crystals. Sodium chloride, the common table salt, consists of a sodium cation and chloride anion. As these ions bind together, they will form a cubic ionic crystal. In our sodium chloride ionic crystal, each sodium ion will be surrounded by 6 chlorine ions, and each chlorine ion will be surrounded by 6 sodium ions. The number of ions surrounding an ion of the opposite charge is known as its coordination number. In our sodium chloride ionic crystal, sodium has a coordination number of 6, and chloride also has a coordination number of 6. Cesium chloride consists of cesium cations and chloride anions, which bind together to form a cubic ionic crystal. In a cesium chloride ionic crystal, each cesium ion will be surrounded by 8 chlorine ions, giving it a coordination number of 8. Each chlorine ion will also be surrounded by 8 cesium ions, giving it a coordination number of 8. Titanium dioxide, because of its ability to absorb UV rays, is used as one of the ingredients in sunscreen. It consists of titanium cations and oxide anions, which will bind together to form a tetragonal ionic crystal, meaning it will have a slightly different shape and, consequently, different coordination numbers than our two previous crystals. In a titanium dioxide ionic crystal, each titanium ion will be surrounded by 6 oxide ions, giving it a coordination number of 6. However, each oxide ion will only be surrounded by 3 titanium ions, meaning its coordination number is only 3. When they are in a solid form, ionic crystals will not conduct electricity. However, if the crystals are melted or dissolved in water, they can conduct electricity. Summary: ionic crystals will be formed when oppositely charged ions are bound together by an electrostatic force of attraction. Sodium chloride forms a cubic ionic crystal, and both ions will have coordination numbers of 6. Cesium chloride forms a cubic ionic crystal, and both ions will have the coordination numbers of 8. Titanium dioxide forms a tetragonal ionic crystal, and the titanium ion has a coordination number of 6, while the oxide ion coordination number is 3.
At this point, you should be able to generate a full and appropriate response to today's essential question. How is electronegativity used to determine which atoms form ionic bonds?